Our interest today in nuclear science is not incremental improvements to existing nuclear engineering, but looking at new pathways that might make light element fission fusion possible in the future. We in the Center for Emerging Energy Sciences, or CESE, are very much involved in looking at material correlates that help with the emergence of new nuclear physics and new nuclear engineering that may lead to a future energy source that produces no nuclear waste. That's certainly not true today, but may be true in the future.
When I first got here at CESE, we were working on CR39, developing it, and this is a nuclear particle track detector, so we can expose it to nuclear radiation, and it will give us tracks that we can then look at under microscopes and analyze. And since then, we've been working on developing new coatings for this that can make it sensitive to different types of nuclear radiation. And then we've also been using AI then to analyze that. So now we have AI that differentiates between, say, alpha particles or tritons. And this can be useful at looking at different types of reactions. And that can be very useful for all types of nuclear experiments.
To do this at a university, we had to develop instrumentation that could work on very small quantities of nuclear material to fit with inside our NRC license. In the process of doing this and developing new instrumentation and new measurement technique, we've found that much of that is applicable to things that are not really central to nuclear energy, but are very useful in, say, looking at ammonia production. We're hoping to find a way to do it electrolytically because that may lead to having a lower carbon impact in terms of energy. We're also involved making respirators and making monitors for human and animal respiration.
One of the biggest projects we've had here lately is the sensor integrated block, and it was developed to look at respiratory ailments. It takes basically a room full of large equipment and compresses it into a handheld device. We're looking at biomarkers, mostly respiratory gases and temperature and other parameters. We're working with a veterinarian researcher, and that's one application that I believe is going to be huge. Specifically, we're looking at equines right now. That's his background. Horses' lungs are very similar to our respiratory systems. And from a human perspective, what we're really hoping is that since we have this in a small handheld device, we're hoping that one day when people go into a clinic, it'll become a new clinical vital. So that's one of our biggest hopes for the technology.
Typical research reactors are going to produce neutrons up to about 8 megaelectron volts. This DT fuser that we have in the bunker at Texas Tech is able to produce neutrons up to about 14 megaelectron volts, about 17% of the speed of light. One of the benefits of this is even though it has a smaller net flux, is that we're able to explore these higher energies and look at some of the fission-fusion reactions that occur at those higher energies. This has applications in medical physics, shielding, damage analysis, and it's a unique opportunity for students to get hands-on experience, and we're really hoping that it helps us train the next generation of nuclear scientists.
When I first arrived at Texas Tech University, I didn't have too much background in nuclear. I was just a general physics major in undergrad, and now I've learned tons about various aspects of nuclear in terms of detection, safety, high energy physics, all these things, and really how different pieces come together from our lab and then other labs that we work with. And it's not just about the old nuclear, which is conventional reactors, fission, nuclear waste. There's a lot of new nuclear, and that's what a lot of people are hoping for.
We are very fortunate to have close collaborations with the University of Missouri Research Reactor and with private industry too in the San Francisco area. We're also very close in collaboration with Lawrence Livermore National Laboratories, especially on our NASA grant to pursue this new fission fragment nuclear rocket engine development.
In our design, the fission fragment itself is a propellant. There is no need of intermediate conversion of energy. So we are able to harness the entire kinetic energy of this fission fragment into propulsion and generate a very high thrust and specific impulse. In order to do that, we have to do this initial testing. And for that testing, we utilize this MRI magnet that was provided by Texas Tech Neuroimaging Institute.
Emerging energy science often requires very specific approvals from regulatory commissions and state boards. One of the things that we've been working on is we have been conducting simulations using Monte Carlo end particle codes and COMSOL physics. And we do those before any experiment so that we can use it in order to predict any sort of results we expect, such as nuclear byproducts and what the quantity of those should be. And it allows us to confirm and repeat this type of validation for every single set of experiments.
We're very excited about quantum nucleonics. It emerged around 2020, 2021, and this is applying what we know at the forefront of quantum mechanics now to understanding nuclear process and controlling nuclear process. As we developed new instrumentation for this new nuclear area, we found that many other research groups across the country and also many companies were interested in applying this to their work as well. So we're very excited about our ability to create a service center to work for other research groups and to work for industry when they have need for what we've openly published in the literature. And that is something that I hope will advance this field very rapidly.